Hello everybody, welcome to the Seren Summer School. My name is Jordan Edwards and I'm going to be teaching you some of the things that I found very interesting about physics when studying it at A-level and further. Just a bit about myself. I come from South Wales in the valleys. Yes, I know I don't have the accent, you'll just have to believe me. I've just finished my master's degree at the University of Warwick studying physics. In October, I'll be starting my PhD at the University of Oxford, focusing in condensed matter physics. Through my lectures, I may pose you some questions. I encourage you to pause and think about the answer before continuing. You may want to have a pen and paper ready just to jot down some notes as we go through our journey. So, what is our first lecture about? Well, our first lecture is all about special relativity, a theory that I think many of you would have heard of before. So, this is special relativity, a space-time odyssey. First off, I want us to ask what, why, and when. So, special relativity is a theory that's used to describe how speed affects mass, space, and time. Later on, we'll find that a more accurate description is spacetime. Now, we use special relativity in special cases where we're dealing with huge energies, high speeds, and astronomical distances. Special relativity is used for physics in inertial reference frames. We'll come back to this later. But an inertial reference frame is just a reference frame that is not accelerating. What this means is that special relativity does not take into account accelerations. So gravity is not inbuilt in the system and we ignore it. So why can't we just go straight to general relativity, which deals with these accelerations? Well, the reason is that we don't have the language at this level to describe non-inertial reference frames, or the accelerations that we need to describe gravity. A fun fact about Einstein when he developed general relativity is that he made sure as a sanity check that his equations actually collapsed down to the familiar Newton's laws that you know. This is just another example of how remarkable the work is that Isaac Newton did at his time. So what do I mean when I say that we don't yet have the language to describe non-inertial reference frames? Well, as you see here, this is some of the scary maths that you might encounter when studying general relativity if you take physics further. The language of general relativity is the language of what's called tensors. As I said, if you continue to study physics at university level, you'll become very familiar with tensors. So, let's start our journey. We start with the historical attempts to tackle relativity. And here, it might be a bit surprising to see the astronomer Galileo Galilei. He was the first to argue that it's not possible to tell if one is moving uniformly or is at rest without any external forces. And this is summarized in his principle of relativity, in which he states that the laws of motion are the same in all uniformly moving reference frames. Some of you may have heard of Einstein's thought experiment about being in a falling elevator. This is actually a reformulation of a description Galileo used about being on a boat on a smooth sea. But what are these reference frames that I keep banging on about, as I don't think you guys have encountered them before? Well, to be quite frank, they are a little bit of a hard concept to grasp. I remember when I was first studying physics at university, I struggled with these concepts. So don't worry if you don't get it first time around. I encourage you to maybe rewatch the lecture or use sources online such as YouTube. I think Khan Academy has some pretty good videos on relativity and reference frames. So, if we consider two reference frames, S and S prime, these are just sets of coordinates from which measurements are taken. especially velocities. For an example, the frame of reference S on the left is taken to be between A and B, and it's stationary with respect to both, i.e. this reference frame is not moving. So what does this mean? Well, this means that all distances are measured relative to the origin in S. So A will be a distance, let's say, minus 2 meters from the origin, and B will be a distance 2 meters from the origin. In the reference frame S, A moves at 1 meters per second, and B moves at 10 meters per second. Okay, so this is one version of a reference frame. Let's change reference frames. Our frame of reference S prime is the frame of reference of A. So, what does this mean? Well, this reference frame is actually moving at 1 meters per second forward in order for A to appear stationary in S prime. So, if we imagine ourselves as A, we are actually stationary in this reference frame. B will be moving forward at 9 meters per second instead of 10 meters per second, and the world around us will be moving backwards at 1 meters per second. S prime is an example of a reference frame that's moving with constant velocity, and S is an example of a stationary reference frame. So, let's just do a quick example about reference frames and how these calculations work. Consider two reference frames, S and S prime. S prime is moving relative to S at 10 meters per second. If S and S prime coincide at t equals 0, i.e. they're at the same location at t equals 0, what distance does the origin of S prime, the moving frame, travel after 2 seconds if we measure it with respect to S? And what is the same as measured in S prime? I really understand that this is a lot of jargon to take in at once, but please try to do this question. So, in S, we would measure the origin of S prime to move 20 meters. This is because in S, we measure S prime to be moving at 10 meters per second away from us. Therefore, after 2 seconds, the origin would have moved 10 times by 2 is 20 meters. What about in S prime? Well, in S prime, we would measure the origin of S prime to move exactly 0 meters. This is because in S prime, we perceive ourselves as being stationary and the frame S as moving with a speed of negative 10 meters per second. Now, a little caveat, this is actually not quite the case. This is an example of a Galilean transformation. Galileo used these transformations as these are the most simple to understand. This only works, and to a very good degree may I add, because the velocity of the moving frame is much slower than the speed of light. Things get a lot more wacky and weird when we approach the speed of light. So, we just saw an example of an inertial reference frame. An inertial reference frame is any frame of reference that is not undergoing acceleration. For an example, if we sit on a bus that's going at a constant speed, this is an inertial reference frame. We perceive ourselves as stationary and the world outside as moving away from us. Therefore, the laws and equations of special relativity apply. However, if we're sitting on that same bus and that bus accelerates, we now change to a non-inertial reference frame because the acceleration is non-zero. Therefore, the equations of special relativity would not apply in this situation. So, what's the problem with light? Well, recall Galileo's principle of relativity. The laws of motion are the same in all uniformly moving reference frames. Well, Galileo found that with his theory, if we have an object that's moving at a speed v prime as measured in the moving reference frame, and the moving reference frame is moving at a speed u with respect to a stationary reference frame, the velocity of the object measured in the stationary reference frame is just the addition of both of those velocities. I encourage you to maybe draw out what this would look like. This was not good to James Clerk Maxwell. Can you think of why? Well, James Clerk Maxwell showed us that the speed of light was a constant. It's independent of the speed of the source and the observer. And this directly contradicts the Galilean transformations. As in the Galilean transformations, if we were to have a flashlight in the moving frame, then the speed of light in the moving frame would be less than the speed of light in the frame that is stationary. Therefore, there are two possibilities that were thought of at the time. The first is that Maxwell was correct, but only in some sort of special reference frame. Or number two, Maxwell was wrong. Now, if you go on to physics at any further level, you'll find that Maxwell being wrong is a very bold statement. So, let's see what happened. In order to fix Maxwell's theory, an existence of the ether was proposed. This is a material that permeates all of space. Light propagates at c through the ether. And for all frames moving relative to the ether, the regular Galilean transformations apply. Now, a fun fact, the ether actually comes from old medieval scientists and alchemy. A very well-known scientist known to dabble in alchemy was the one and only Isaac Newton. That's very interesting to me. So, let's see what scientists did to try to find the ether. Well, the big experiment in special relativity was the Michelson and Morley experiment. We know that the Earth moves relative to the Sun at 30 kilometers per second. This means that we will be moving through the ether. So, if we look at the setup on the left-hand side, we have a light source that's shooting a light beam to a beam splitter that splits the beam into two directions, given by the blue arrows. Now, if we are moving through the ether in our reference frame, that is perceived by us as there being some sort of ether wind, a dragging of the ether. So, what would happen? Well, with the Galilean transformations, the speed of light along the ether wind would be different to the speed of light against the ether wind. Therefore, when we superpose the light from the orthogonal mirrors, we will have a phase difference that could be measured at the detector. So, what was actually measured? Well, there was actually no difference whatsoever. So this meant that there was no ether drift and no ether wind, and therefore the ether theory kind of collapsed overnight. Well, this suggests that Maxwell was not wrong. Something strange was going on. Scientists at the time tried to come up with many explanations to keep the ether theory alive. Albert Einstein did not do this, however. One of the very interesting facts about this experiment that I find is if you see the experimental setup on the right-hand side, that entire setup is floating on a huge bed of mercury, which is just crazy in terms of health and safety. So, here's where our boy Albert Einstein shows up. In 1905, he decided to start from two postulates and see where it took him. The first was that all laws of physics are the same in all inertial reference frames. And the second was that the speed of light in vacuum is the same in all inertial reference frames. As we can see, the first relativity postulate is an upgraded version of Galileo's principle of relativity. The second relativity postulate was from Maxwell, when he proved that the speed of light is a constant. So here is where it is a good time to introduce the space-time continuum. Space-time coordinates are very similar to the spatial coordinates that you are familiar with, but extended to include time. We denote space-time coordinates by t, x, y, and z, or much more commonly, we times the time coordinates by the speed of light. This allows for our calculations to drop out with factors of c and make them a lot easier. The concept of spacetime is needed to define events that happen. Knowing when something occurs is equally as important as knowing where it occurs. So an event is a localized occurrence in space and time. A great example of an event, if you're struggling to visualize what it would be something like sending a light pulse or receiving one, or an explosion, or a firework, just something that's localized in space and time. Now, spacetime was a concept that was developed by Hermann Minkowski, and Einstein actually didn't see a use of it when Minkowski first introduced it to Einstein. So, now let's look at some spacetime diagrams. The diagram on the right is an example of a spacetime diagram. This might look a bit weird to you because the convention in spacetime diagrams is to put the time coordinates on the y-axis. Now, if we think of relativity postulate 2, we know that the speed of light is a universal speed limit. So, we can draw light lines on the diagram. What would they look like? Let's see if you can draw them. Well, yes, they're actually lines with gradient plus and minus 1. So, what can we do with this? Well, we can draw some space-time diagrams. A, B, and C on this diagram are known as events. A is in the future and it can affect you, since it would take a velocity less than the speed of light for the information to reach you. B is in the past, and C is inaccessible, and that's because information would have to travel at a velocity greater than the speed of light in order to reach you. An example of an object moving through space to the right at a velocity in between 0 and C is given in green. This is known as a world line. So, now we've seen some space-time diagrams, let's see some consequences of these. I ask you, can events be simultaneous in two reference frames at the same time? Well, consider three equally spaced observers, stationary in a frame S', but moving at a constant velocity in S. At Ct equals 0, observer B sends a light pulse to observer A and C at the same time. In S', these events are simultaneous, and the observers A and C receive the light pulse at the same time, as shown by the red dashed arrow, line. Consider now the same events in S. What do you think happens to the world lines of A, B, and C? Well, since they are now moving with a constant velocity, the world lines are slightly tilted to the right. Not at 45 degrees, because 45 degrees is reserved for our light. So, in S, we see that the events are not simultaneous. There's been no trickery here. In the frame of A, B, and C, the events are simultaneous, and they receive the light at the same time. However, to an observer who's stationary with respect to these three observers, A receives the light well before C does. The events are not simultaneous in S, but they are in S'. This is a massive thing to understand in relativity. things are relative. In general, events are not simultaneous in different reference frames. In a later live event, we'll go through an example of this in mathematical terms and see what the consequences are. But this is something that blew my mind in first year. The fact that in one frame of reference, events can be simultaneous, but in another, they are not. So, now we know a bit about spacetime, we can talk about the correct coordinate transformations to get from one frame of reference to another. These are laid out by Lorentz in his famous Lorentz transformations. Lorentz is the guy on the right-hand side, as you see, and there's a pretty funny story in physics. He's not the only Lorentz. There is a Lorentz with the T in the last name removed. This leads to a lot of physicists to say that he was one T away from greatness, because this Hendrik Lorentz is a lot more famous. So, the Lorentz transformations are motivated by the Galilean transformations. They're linear, but they also satisfy x equals ut for x prime is equal to 0 as observed in the reference frame S. Now, the primes are the quantities measured in the reference frame S prime, and the non-primed are the quantities observed in the reference frame S. So, Galileo's transformation is x prime is equal to x minus ut. Lorentz's is x prime is equal to gamma x minus ut. This gamma is just a function that Lorentz put in order to get the correct transformation, and then he found what this function was. So, I encourage you to think of what the corresponding relation would be for x. It's not simply rearranging this equation. You need to do something extra, because we are changing frames when we are trying to rearrange. A hint is to think about what the velocity does when we change frames. Well, if we rearrange the previous equation for x, it's not enough on itself. What we are doing is changing frames. By changing frames, the speed of the other frame flips direction. And as you can see, the corresponding equation is x is equal to gamma x prime plus ut prime. The eagle-eyed among you might also see that this is actually equivalent to running time backwards to swap the frame S prime. So, with this new equation, we can actually rearrange this for x prime and substitute it into our previous equation for x prime to obtain a relation linking t and t prime, the times recorded in the two reference frames. We get the equation on the bottom. As you can see, if the gamma factor, Lorentz's gamma factor, is not equal to 1, the time in the two frames is different. So, Lorentz found what this gamma factor was after some very meticulous calculations. He found that the gamma factor is actually 1 over the square root of 1 minus u squared over c squared, where u squared is the velocity of the moving frame. This is a very important result and is used all over relativity and quantum mechanics, even until the 4th year of university study, I may add. So the correct transformations were then seen to actually be the ones shown on the screen. Now these are some very important equations, so I would encourage you to jot these down on a piece of paper, because we will be using these in a future live event, and we'll also be using them for some further explanation in this lecture. So, one of the consequences of special relativity and the Lorentz transformations is length contraction. If we consider a bar at rest in a reference frame S prime that's moving at positive u in the positive x direction in a stationary reference frame S, the coordinates of the end of the bar are given as such. Remember that this first entry is actually the time entry. The length of the bar as measured in S prime, where the bar is stationary, is given by L prime is equal to LB prime minus LA prime. So, we're actually concerned with what the length would be in frame S, the frame in which the bar is moving. To determine this, we need to measure what the x position of the ends of the bar are simultaneously, because obviously it's moving in S, so if we aren't measuring it simultaneously, we'll just get a null result. So, we want to recall the Lorentz equations relating the x coordinates between frames. And for convenience, I put them up on the screen. As I just mentioned, we need to measure the ends in the reference frame S simultaneously. So TA is actually equal to TB, and let's just say that's equal to T, just to simplify. Well, if we take the XB prime equation with this and take it away from the XA equation, or the opposite way around, actually I've done it, then we obtain XB prime minus XA prime is equal to gamma XB minus XA. So what this actually means is that the length in the reference frame that the bar is not moving is equal to this gamma factor times by the length in the reference frame in which the bar is moving. Now recall that this is for a bar that is stationary in the reference frame S prime. I encourage you, if later on you want to repeat this calculation for the bar that is stationary in S and moving at negative U in S prime. And a hint, it is not simply this equation rearranged. So, in general, we can actually say that L0 is equal to gamma LU, where L0 is the length measured in a frame where the object is stationary, and LU is the length measured in a frame where the object is moving. An example of this can be illustrated very well by considering ultra-high velocity cosmic ray protons. These have a gamma factor of 5 times 10 to the 10, which is absolutely huge. As a quick exercise, if you'd like, take the gamma factor and take this value of 5 times 10 to the 10 and work out what velocity the proton would have to be traveling at to get this gamma factor. If our galaxy is 100 light years across in a stationary frame, what length does the proton observe the galaxy to be? I'll give you some time to think about this. Well, we use the equation at the top, and what we want is LU. LU is the length measured in the frame where the object is moving. So, for the proton, LU is going to be the length of the galaxy divided by its gamma factor. And this actually turns out to be 1.9 times 10 to the 10 meters. That is crazy. To put this into perspective, this is just 13% of the distance from the Earth to the Sun. So, a galaxy in a stationary frame that's 100,000 light years across, to that proton, is seen as only 13% of the distance from the Earth to the Sun. Note that length contraction is reciprocal. Each observer actually observes the other bar contracting. This is because neither is wrong. There's no true or correct frame of reference. So another very cool consequence of special relativity is time dilation. Now, in a very similar way to length contraction, we can obtain an expression for time dilation. Here, we consider the ticks of a clock. delta TU is the time where the clock is moving with respect to the observer, and delta T naught is the clock that's stationary with respect to the observer. So what is the consequence of this equation? Well, the consequence of this equation is huge. This means that time is relative. You actually experience your own time. You are the only person who experiences time the way that you do. This means that if you were to blast off in a rocket at close to the speed of light, you would be experiencing a different amount of time to a friend that is stationary with respect to you on Earth. That is absolutely crazy. So let's see a big example of this, and let's go through some of the maths behind it, because I think that's very interesting. So this is the twin paradox. Now, Alice and Bob are twins. Alice goes on a journey to a star 30 light years away, travelling close to the speed of light. For her, the trip takes less than 1 year. But she returns to Earth to find that Bob has aged over 60 years. But in Alice's rest frame, Bob is the one that actually travelled. She remains stationary, so shouldn't Bob's clock be the one to run slowly? They can't both be younger than each other. Remember that there is no true reference frame. The solution of this lies in identifying the frames and the events that are relevant. And we should note that the acceleration and deceleration in the twin paradox in special relativity occur instantaneously. This is in order to cut out any non-inertial reference frames that we may have. So, in the twin paradox, we actually have 3 inertial reference frames. The first is Bob's reference frame, labelled S. The second is Alice's outward journey rest frame, S prime. And the third is Alice's inward journey rest frame, S double prime. We should also note that there are 3 events. The first event is when Alice leaves the Earth at x equals x prime equals x double prime equals naught, i.e. all of them coincide at t equals t prime equals t double prime equals naught. Now, the second event is where Alice reaches the star. The star in Bob's rest frame is at x equals L away, and it takes a time in Bob's rest frame, t equals L divided by u, just distance divided by speed. Now, there is a third event where Alice returns to the Earth. Her x here is 0 because we define the Earth at x equals 0. The time taken in Bob's rest frame for this to happen is just 2 times L divided by u. So, from event 2 to event 3, Alice is actually swapping rest frames from S prime to S double prime because the speed is changing direction. Alice goes from an outward journey to an inward journey. So, we need to figure out the time in S prime and S double prime for the relevant events. To do this, we use the Lorentz transformations in Alice's frames. So, here we have the Lorentz transformation for S to S prime and for S to S double prime. As you can see, the only difference between these two equations is the sign between the time and the second component, and this is because the velocity changes directions. So, we want to draw up a table of what's actually happening. Seen here is a table of all the frames and events that we care about. The 3 relevant frames are S, S prime, and S double prime, with the associated times t, t prime, and t double prime. And as we saw on the previous slide, there are 3 relevant events that we care about. Event 1, which is Alice leaving the Earth. event 2, Alice arriving at the star, and event 3, Alice returning to Earth. So we care about the times in the relevant frames. So let's start in Bob's rest frame. Bob's rest frame is S. Event 1 occurs at t equals 0 for all of the frames. If the star is at a distance L away and Alice travels at a speed u, then event 2 occurs at L divided by u, which is just distance divided by speed. Event 3, Alice returning to the Earth, is then just double this time, because she's doing the same return journey. What about in S prime? Well, Alice actually has two relevant frames, S prime and S double prime, so we need to pick out the relevant events in each frame. The relevant events in S prime are event 1 and event 2, because between event 2 and event 3, Alice swaps from frame S prime to S double prime. So, event 1 also occurs at t equals 0 in S prime. But what about event 2? Well, we're now in S prime, so we need to use the Lorentz transformation from frame S to frame S prime in order to figure out what time Alice experiences in S prime. Shown on the bottom left-hand side is the Lorentz transformation for S to S prime. Therefore, we just have that t prime is gamma t minus ux over c squared, where the time is just L divided by u, and x is L, because the star is at a distance L away. I've just put event 3 in for completeness, but event 3 isn't actually needed in the frame S prime. Okay, so when Alice then turns around to come back to the Earth, she changes from frame S prime into frame S double prime. So the relevant events here are event 2 and event 3. As you can see, to change from frame S to S double prime, the Lorentz transformation is very similar. The only thing different is that we do not have a negative sign in the middle, we have a positive sign. And this is because the velocity flips directions. Therefore, the time for event 2 to occur in S double prime is at gamma L divided by U plus UL divided by C squared. And in event 3, it's gamma 2L divided by U plus U divided by C squared times by 0. Because remember that Earth is defined at x equals 0. Therefore, we end up event 3 in S double prime occurring at a time 2 gamma L divided by U. So, now we have all of these, let's figure out what the time elapsed is. So, the time elapsed for Bob is just the difference between event 2 and event 1 and event 3 and event 2 in Bob's rest frame. This is just 2L divided by U, which makes complete sense because Bob is just perceiving Alice to travel 2L at a speed u. But what about the time elapsed for Alice? Well, the time elapsed for Alice is going to be a combination of the time in frame S prime and the time in frame S double prime. Remember the relevant events. The time spent in S prime is just the difference between the event 2 and event 1 in S prime. And the time spent in frame S double prime is the difference between the events 3 and the events 2 in S double prime. I encourage you to try to go through the maths yourself and maybe think about why this is the case. So we then get a time elapsed for Alice to be 2L divided by gamma U. This means that Alice experiences less time than Bob by a factor of gamma. This is entirely because Alice changes frames, but Bob does not. This is really interesting. They were twins when she left, but when she came back, she was a lot older. And this is the maths behind why. It's all to do with this gamma factor and the fact that the speed of light is constant in all inertial reference frames. So, this is the end of the lecture. I wanted to make this one a little bit shorter because I know that we covered a lot of ground and some of these concepts might be very hard to grasp. I know they were hard to grasp for me for the first time. But what else is there? Well, we haven't gone through topics such as velocity addition. Obviously, the Galilean velocity addition was incorrect. So what is the relevant velocity addition for relativity? We haven't gone through the relativistic Doppler effect. I think you have either covered the Doppler effect or you may cover the Doppler effect in your second year of A-level. But this changes when you are approaching the speed of light. Another thing that we haven't touched upon yet are the energy and momentum relations. The big equation that everyone knows, E equals mc squared. We haven't been through that yet. And even that is just a simplification because the entire equation is E squared equals P squared C squared plus M squared C to the fourth. So there is a lot more to study, and if you do enjoy this topic, I really encourage you to look for more videos online. So that's the end of my first lecture. I hope you enjoyed, and if you have any questions about special relativity, physics in general, or you just want to talk to me about some university life or any general questions, then please either email me or we can set up a small Zoom call in the future. So yes, give yourself a pat on the back because we did a lot. We covered a lot of ground in special relativity. So thank you very much for listening.